Okay, we're heading into the home stretch here, and we're still talking about diaphragm and specifically diaphragm modeling. One of the situations that I want to draw your attention to is quite important in your analysis model that we see engineers making this mistake many times. And I'll show you one situation where it could be catastrophic if you're not careful. As you all are aware, many programs like ETABS assume a infinitely rigid diaphragm as a means to reduce the number of degrees of freedom of the system and therefore cut down on the model, the unknowns, if you will, in the model to reduce the solution time. And when this first started occurring some years ago, it was a real boon to modeling because you could model more complex situations and much faster than before. So it's certainly a good idea, but it brought with it some potential problems that the engineers need to be aware of. First of all, if you have a rigid diaphragm assumption in your analysis model, anything you connect to that diaphragm will be itself infinitely rigid and therefore undergo no axial shortening and therefore receive no force. And that includes things like collector beams, brace beams that we talked about earlier. And what this slide is all about is cautioning you about the brace beam situation. Brace beams, remember, are those beams that are inside the brace frame system that are receiving all these diaphragm shears and therefore are wanting to shorten and undergo an axial deformation, which in itself is one of the contributions to the story drift at that floor. And if you don't release that brace beam somehow from the diaphragm, you won't capture the forces correctly and you won't realize the deformations correctly, and you'll get erroneous or partly erroneous results. So we know from experience that if you were just looked at the deflection of a braced frame, that a certain amount of that, the deflection in that braced frame is coming from the shortening of the columns, right, like cords of a truss. Part of it's coming from the shear deformation of the webs or the braces, right? They undergo PL over AE, shorten. That contributes to some of the shear racking of the story. Another component comes from that brace beam. It shortens and moves the whole frame over. That can be as much as 15% of the total drift of that frame. And if you've connected that brace beam to your diaphragm and the diaphragm is infinitely rigid, guess what? You've miscalculated, or you have ignored effectively that component of the drift of that frame. So this can be important not only in your drift calculation, but it can be important in the proportioning of the brace frame beam itself. You're not capturing the force that you might think it's getting, and therefore you either got to go back and do it by hand, or God forbid you don't know that it's not doing it right and you don't use the right forces, then you're of course under designing that beam. So how you release these brace beams from the diaphragm becomes a very important part of the challenge of modeling these multi-story buildings. It's easy now, instead of using just always assuming that your diaphragms are infinitely rigid, it's possible to model the diaphragm using in-plane shell elements. And that might be a good way to go because you can use a fairly crude mesh there. That is, it can be 30 feet wide and 30 feet long in your mesh. But if you model it as a shell element, you then can use it as a tributary collector, if you will. It can collect the gravity loads, and if your program's set up to do that, it can carry that load over to the beams in the column and the beams that frame into those columns, so that's an advantage. In other words, it picks up the tributary loads correctly. But more importantly, you capture the deformations and the stresses in the diaphragm itself to see if you have any diaphragm shear problems. or any hot spots in your diaphragm that you might otherwise be unaware of. So you can either do this, you can assume an infinitely rigid diaphragm and do all this by hand, or you can model the diaphragm itself. And more frequently we find ourselves modeling the diaphragm because it's pretty easy to do now. And unless your problem is really big, it really doesn't tax the computer power that much. Always be mindful of the load path of the forces in the diaphragm, and be sure that you've created a load path that's valid, that's realistic, and that gets the loads to where they need to go. So if you're going to model the diaphragm, then you want to be sure you model the drag struts or the collector beams as well, so that you can see what forces you're getting in there. So once you start this, go down this path of modeling the diaphragm, you of course got to do it correctly and capture all the elements, including the collector beams and the drag struts. You can also model flexible diaphragms as membrane elements. I've always seen it done as shell elements, but I understand you can also do it as membrane elements. And there's different programs that have different ways of doing it, so depending on what your favorite program is, you may want to research this to see how it's done. I know RISA does it now, and I know STAD does it, Georgia Tech Strudel, SAP, and ETABS, and all the good programs I think have this capability now. Now, it's very important that you capture the axial force in the brace beam correctly, and that's what this slide is supposed to show you, that the force in the brace beam, that's the beam now, the horizontal beam connecting the two columns at the top of the chevron, it's receiving load from above through the braces, right, that come into the column joint, and it's also receiving load from the floor itself as a collector. It's collecting shear, if you will, from the diaphragm. So what we're trying to show you here is that you've got to create the free body diagrams to be sure you're collecting these forces properly into the brace beam, particularly if you're doing this by hand. And depending on whether you have a chevron brace or a diagonal brace, as we have in this case, obviously the load paths are different, but the concept is the same. Be sure you're getting the right forces from the diaphragm and the brace above into your collector beam. In this case, obviously, that collector beam here is receiving the horizontal component of that brace plus the diaphragm shear it's collecting along the floor. And that's why that axial load diagram, which is what this is collecting, it's growing from 142 kips, which is the horizontal component of the 200, plus the line load of 7.1 kips per foot, that over the 10 feet of width gets you the 213 kips. So be mindful of your statics. And this is, again, this is a close-up to show you what's going on there from the brace above, transmitting its force into the horizontal brace beam, and then also collecting it from the floor system. And here's the axial force equation, sort of in analytical terms. So rigid diaphragm, no relative in-place displacement at the joints. Be real clear about that. No deformation. That means no force. Beams with both end joints connected to the rigid diaphragm will not have any axial force. If you design that beam using a post-processor as part of the program, you're not going to get any force in that beam, and therefore you won't get a correct design. If you go that way, then you got to design that brace beam by hand, by statics. You got to get the force in the brace and then manually calculate what the forces are in the brace beam to design it. And remember that you also may be missing as much as 15% of the drift in the frame because of that assumption. If you're going to release joints, which is probably what you want to do, you got to be careful you don't release too many joints, or otherwise you'll create an instability in the model and it won't even run. So there gets to be a little bit of an art to modeling diaphragms and their connections to brace frames or moment frames. This slide basically says, okay, if you're going to connect the diaphragm to the joints, the beam and the column and the brace joints, as rigid elements, then the brace beam isn't going to receive any force. It'll show zero. And in this condition, you probably don't want to model it this way, but if you do, recognize you got to do statics to collect all the real forces in that brace beam. An alternative to that is to discretely release from the diaphragm, from the rigid diaphragm, certain joints that then allow this deformation to occur. And if the axial deformation occurs, then the force will show up. So this is what you would do if you were able to collect all the diaphragm shear along the brace beam itself without having to worry about the collector beams on the sides, as we talked about earlier. Then this would be a way to go. You would release those two joints where the brace connects to that beam with the X through them. That's a joint release. If you did that, you would get force, as shown in the red and the yellow shading there, in those elements that would be correctly depicted. If, however, you can't collect all the shear within that brace beam because the shear is too high for the diaphragm, then you may have to use a collector beam in front of or behind the brace frame like we show here, and then in order to get any force into that member, you have to release this joint so that that beam can shorten. So I think you see what we're trying to do here. We're trying to get you to release the proper joints discretely so you can realize the deformations and therefore realize the forces that are in those members, so that if you use a post-processing element as part of your program to design those, it's designing them correctly. There are many engineers that wouldn't even know about this, and they would just, the program would say you need an 18 by 35 beam there, and probably what's happened is that the program has designed that 18 by 35 for the gravity load on it, and has totally ignored all of the axial load in that brace beam. And if the engineer is not smart enough to realize what happened, he'll write W18 by 35 on the drawings, and that's what will get built. So these are the things you have to be careful about when you're doing your modeling and you're doing your design of the lateral load resistant system when it's combined with diaphragms. So this just tells you that the different situations that we just talked about, approach number one or approach number two, you handle it depending on what the magnitude of the shear forces are in the brace beam. This same situation we talked about earlier for the chevron brace also applies to a diagonal brace here. Again, if you have no releases, there'll be no force in the brace beam. And if you get a post-processor to design it, it'll say it's an 18 by 35 and it's designed only for the gravity load on it. And that would be wrong. To do it correctly, then, you want to release one of the joints, as we show here, where that X is. That allows the shear that's getting into that beam to deform the beam because it's disconnected from the diaphragm. That means it'll realize an axial force. If you get your post-processor to design that, it won't be an 18 by 35. It'll be a 14 by 120 because now it's got a lot of axial load in it in addition to whatever gravity load it had on it. So, again, be careful of the load path. Here's the same releases that you'd have to do to have a collector beam here. If you couldn't carry all of the shear along that length, you'd have to drag it in to this, and here's the joint releases that you would have to do that. So, flexible diaphragms can be modeled using in-plane shell elements, as we talked about earlier. The beam axial force is not only comes from the force that the program says is in the beam itself, but the shell element is also collecting axial force. So to get the correct force in the beam, you have to collect the force from the shell element to get the right axial force in the beam. So be careful of that. Your program may not automatically add those two up. You have to do that yourself. That's what this slide is trying to say. Now, we want to go through a series of slides here quickly that just identify for you some cases to look out for. A little bell goes off and says, this could be a problem. Obviously, here we got a big stair opening, or maybe we have a mezzanine or something opening, and we got a lateral load resisting system, and the only place the floor connects to it is right there. Well, obviously, we've got to be concerned about how does the diaphragm shear get its way into this vertical lateral load resisting system. Right now, this is the only available path, or possibly through here and then down this way. Both of those may create high shear stresses in that dapped area, if you will, of the diaphragm. You may have to put extra reinforcement in there. It's kind of like a coke beam. Another common situation happens in the middle of buildings that have big atriums. You got this big roof atrium opening. All your lateral load resistance is on the ends. And the diaphragm has to span from one end of the building to the other end of the building. And guess what? You got this big hole. So what does that do? It's kind of like a Vierendeel now, right? It's kind of like a Vierendeel truss, where this little piece right here is acting like the chord of the Vierendeel. That's the top chord, that's the bottom chord. And you get additional bending in the diaphragm from those Vierendeel stresses. And therefore, you're probably going to have very high localized shears, and you'll probably have to put a lot of reinforcing steel in that slab to account for that Vierendeel effect, as I would call it. And then you got to be careful that you can transfer all the shear at the end there, where it says high shear. You're going to have some real high shear stresses right at that point. This is a situation that I'll never forget. We did a peer review on a multi-story building. And it's common in a lot of the bottom floors of a multi-story building. You got a lateral load resisting system around the perimeter. And you got this big atrium. Maybe this is a 3-story space or a 2-story space. In the middle of the building, there's the elevator core. And that might be a mezzanine floor used for storage or closets or whatever. All the elevators are inside there. Now, we've actually seen a situation where the engineer designed this column right there, or that column right there, and all of these columns that might have as much as 12,000 kips in them if this is a 60-story building, or even more. He designed that column as if it were braced at the floor above where there was a full diaphragm, and at this floor. He took that point as a brace point for that column. So the question I would pose to you is, what is providing the bracing in this mezzanine floor to that column? If there's no vertical bracing in the core, the answer is nothing. The column really is not spanning from the floor below to this mezzanine slab. It's spanning from the floor below up above, through the mezzanine floor down to the floor below. In other words, it has twice the unbraced length that that guy thought it did. And had that been built, instead of carrying 12,000 kips on a 20-foot column, it was carrying 12,000 kips on a 40-foot long column. It would have just buckled. The answer to that, of course, is there probably should have been some vertical bracing locally within this core to provide this floor as a brace point, but he didn't have that. All the lateral load resistance was around the perimeter. So this is just one of those situations where, being aware of what's bracing what is important, and recognizing some of the pitfalls of having a big open diaphragm should cause you to think about unbraced lengths and what's the load path? That's always the question you want to ask. Here's another situation that we've seen. Elevators on both sides of a vertical lateral load resisting system, and the engineer went about and modeled the 3 walls here as the lateral load system. never checked to see how the diaphragm shear got into that middle frame, which has a hole on each side. Well, the only way that frame can ever receive any load from that level is through the collector beams on each side, the yellow dotted line there. And if the engineer didn't recognize that as the load path, he would have a lot of additional axial load in those yellow broken beams there that he didn't even know he had. They're really acting like beam columns. They're collecting gravity load and designed like a floor beam, but then they got a lot of axial load in them because that load's being delivered to the vertical lateral load resisting system. So another situation you got to be careful about. Whenever you're doing a high-rise building and the architect is gracious enough to give you a shear wall or a brace, you got to be sure that there's some floor around the brace for the load to get there. They're great at giving you places to give you braces where there's no way to get load to them. So you got to explain that to them and say, well, you know, this location doesn't really work for me because guess what? I don't have any way to get the load there. So it's part of the negotiation with the architect. Lots of L-shaped buildings out there where the lateral load resisting system is here and over here. And you may get a neck down condition there where you get very high shear stresses in there and bending in that diaphragm. Obviously, we've exaggerated a little bit for this case, but I think you get the point. Got to be aware of what's going on with the diaphragms. They're very key elements to the lateral load resisting system. Lots of T-shaped buildings out there. In Las Vegas, they do tons of these. Or Y-shaped or T-shaped buildings. And many times the lateral load resistance is out at the edge, and it creates very high diaphragm shears that you have to consider. You wouldn't want to design this building as a rigid diaphragm. You'd want to model the diaphragm as a shell element to really see what the deformations are and what the shear stresses are in that diaphragm. This is the one that just absolutely can be devastating. We actually saw this on a set of drawings that we reviewed in a peer review. The engineer had designed a transfer truss to carry multiple floors, and notice there's no column below. So this truss is a transfer truss picking up all that column load over to here and to there. In the design of that truss, the engineer used a post-processor that was part of ETABS. And we looked at it and we said, gee, the chords were like 14 by 400 series. And then we looked at his chord, or his diagonals, were 14 by 400, really heavy shear, because they were picking up a lot of columns. And this was like a 60-story building, by the way, so a lot big, heavy column load. And then we looked at his chord forces. And his chord force right there was a 14 by 90. So we said a 14 by 90 chord with a 14 by 400 diagonal. That doesn't look right. And we said, what's going on here? And we finally figured out that what this fella did, he designed that truss, and he forgot to release the truss joints from the diaphragm. So this truss was behaving like it had an infinitely rigid chord, which was the infinitely rigid diaphragm. It was still getting the right shear because the shear had to get over to the end column. So the diagonals were designed properly for the shear force, but the chords weren't designed properly because they were connected to the rigid diaphragm and never got any axial force in it. So the size he was getting was coming from the floor gravity load, not from the transfer truss. And he didn't catch that. Nobody caught that. So if that thing had been built and the contractor had taken out the shore underneath that column, the truss would have just collapsed. So and all this comes from the modeling, modeling assumption, and the failure of the engineer to understand statics, basically. So, you know, when you look at a transfer truss like that, it's carrying 12,000 kips of column load, you should be asking yourself, okay, does this truss make sense? You know, does it have diagonals that are carrying the shear? Does it have a cord that's carrying the compression forces and a tension cord that's carrying the tension? And do the sizes look right? Nobody bothered to do that. They just, that's what came out of the computer. By God, it's got to be right, so that's what we put on the drawings. So this is some of the fear that we managers and those that are responsible and put our stamps on the drawings, right? These are some things we got to think about when our young engineers are designing this stuff. Be sure that they're doing it correctly. I mentioned this earlier. This is a very critical situation you always want to be mindful of. You've got a lateral load resisting system here. It's coming all the way from the roof down to the foundation. This one is coming down from the roof to the second floor, and then all of a sudden the architect said, no, I can't give you a brace here. You're going to have to move it over to here, because he wanted a big lobby there. And so the engineer said, okay, I'll move the brace frame over. And now all the story shear that's coming down this frame gets to this floor, and all of it has to be drug over to here before it can continue its load path down to the foundation. The only way it can get over there is through the diaphragm. And if you have a 14 by 500 chevron brace coming down, you take the horizontal component of that, and that's imparting a shear force into that diaphragm. And if you're not capturing that properly in the diaphragm, obviously it isn't going to work. So this diaphragm in this case would have a lot of reinforcing steel in it, or it might even have to have steel members underneath the concrete slab that provide that diaphragm, horizontal diaphragm capacity. But again, your computer model might not tell you that if you didn't model that offset correctly. So here it is in 3D. Here's your vertical brace coming down. The architect says, no brace. I'll give you one here, or I'll give you one there. I won't give you one here. So the diaphragm has to carry it all the way over to there. And huge diaphragm shears develop then in that green plane. I think most people would probably recognize that and design for it, but it's just one of those things. You've got to be sure you know what's going on there. Another problem we've seen commonly in high-rise construction is when there's a basement, one underground basement or two underground basements. The engineer carried the vertical lateral load resisting system all the way down to the foundation, and he said it's conservative to ignore all the perimeter basement walls. I'm just going to design that load to go straight down. And then he took the ground floor diaphragm right here, and he proceeded to detail that where the diaphragm concrete slab went over the top of the concrete wall, basement wall, and is doweled all the way around the perimeter to it. Okay, now when he did that, in his mind he had one load path in mind, all the story shear coming down all the way to the foundation from the core vertical system all the way down to the foundation. But in reality, the way the building wanted to behave is that, okay, these braces here are now being supplemented with these perimeter basement wall system, which is tremendously stiff. Visualize a 14 or 16-inch concrete wall all the way around the perimeter of a block, rigidly connected by the diaphragm to the top of that. So now what wants to happen is all the story shear that's coming down the building, instead of going down here like the engineer assumed, it's going here, and it's about 3/4 of it's getting sidetracked and trying to go over to the basement walls, which are very stiff elements trying to carry it. And if you don't recognize that, you can literally tear up a diaphragm, probably not in a wind load condition, because you probably wouldn't ever get your 50-year design storms. But by gosh, in an earthquake, if you got an earthquake in this building, if this were in a moderate seismic zone, you would probably just tear up that diaphragm where it connected to the basement wall, and you would have a real mess on your hands in terms of a structural problem. So again, recognizing the load paths and having that load path be consistent with the assumptions you make in your model, computer model, is a very important part of being a good analyst in modeling these situations. So to sum up all the things we talked about, diaphragms, this is Dave Letterman's top 10 problems here. What are the top 10 reasons why you may have diaphragm-related problems? Well, number 10, diaphragm shear capacity never checked. The engineer didn't even know enough about diaphragms to know that there was shear in the diaphragm. Number 9, connections are not designed to transfer cord and collector forces. Number 8, force transfer from the diaphragm to the collector beams and the vertical lateral load resisting system is not considered. The load path never clearly defined. Number 7, cord and collector beams are not designed properly. No recognition of the fact they have shear forces in them. Most of the time, diaphragms are not modeled in any analytical model, therefore the engineer doesn't have a clue about what's really going on. Number 5, axial force in the beams is incorrect because he failed to separate the brace beam from the diaphragm. Large openings in the floor are not given proper attention, therefore high shear stresses in the slab ignored or overlooked. Number 3, building has basement walls and these walls are ignored, thinking it's conservative to ignore them. Maybe not conservative. Number 2, some of the vertical lateral load resisting elements do not go all the way to the foundation but transfer into plan. The engineer failed to recognize the horizontal shear transfer and under-designed the diaphragm situation for that case. And the top number 1 offender, the computer analysis results do not tell the engineer if there's a problem. Garbage in, garbage out. You know, these programs only do what you ask them to. Okay, that wraps up diaphragms. Any questions about diaphragms? I think, once you understand what a diaphragm is and how it behaves, you start to recognize situations that can get you into trouble, and hopefully that will keep you out of trouble.